So we've been talking about the fact that the crust of the Earth is constantly moving around, this idea of plate tectonics. And these pictures that I have here, these two pictures are showing a couple of the end results of that process. So this first picture that you see right here is an example of the crust being folded. You can see kind of these up and downs here. And this is because of one tectonic plate moving this way and another tectonic plate moving this way, and the rocks literally being kind of squished there. You might remember when we talked about the idea of metamorphic rocks and how they get kind of bent and deformed because of a lot of heat and pressure. Well, this is an example of that right there, this idea of these layers being kind of bent and deformed. This is another example of it down here of something that happens, and this you may have heard of. This is San Andreas Fault in California, and this is an area where two plates are coming together, two tectonic plates. You have the North American plate, which is kind of moving this way, and then you have the Pacific plate, which is kind of moving that way. And when this happens, you end up building up a lot of tension here. If you take your two hands right now, kind of put them together like that, and push them together really hard and try to move them, one up and one down, what you'll notice is that they kind of like stick together and then all of a sudden they kind of come apart. Well, that is what happens when you have an earthquake. Don't forget that red slides are where you have to take notes. You should have your notes handout ready to go. Don't forget to look for the owl and let me know where he is. And remember to fill in all of this stuff that you see here. So before we get into this idea of earthquakes, we need to talk about these things called faults and folds, okay? And so you can see kind of an example of actually both of these ideas happening here, where rock can get bent and folded like that, and then sometimes, like in this area here, it can actually get cracked if you try to bend it. Movement of the tectonic plates against each other causes the plates to fault and fold. So let's take a look at this here. Well, in this picture we have a fault, and what you can see here is that there is a crack here in the rock, but if you look at the layers, right, let's look at this layer right here. Okay, if you look at this layer right on the other side of the crack, it's kind of moved up a little bit. So you can actually see that the land has actually moved in the directions of these arrows, up on the right side of the crack and down on the left side of the crack. Over here, we have what's called a fold, and you can see that it's kind of folded over there, right? Folded like that. So a fold, let's start with that. A fold is a collision of crust that bends the rock layers and is causing stress there. Okay, so this is the creation of stress happening. Just like when you were holding your two hands together and trying to get them to move, you're sort of building up tension there and building up stress. Here's another example of it. This is a great picture where you can see some really big folds happening there in the side of that mountain. So we can have basically two types of folds, and this is pretty simple. You can have an anticline, which is, think of that as like a frowny face. These are the folds that go that way. And then the opposite of that is a syncline, and that's like a happy face. The fold goes that way. So we can talk about anticlines and synclines. All right, what type is that one over there in the circle? Is that an anticline or a syncline? It's a smiley face, right? So that is a syncline. Hopefully you got that. What about that guy over there? Yeah, we got another frowny face, anticline over on that side. Okay, so make sure you label the anticline and the syncline on your picture that you see, the picture that looks just like this. So which one's the top one? That's an anticline. And which one's the bottom one? That is a syncline. Okay, so this all has to do with this idea of converging tectonic plates, and we talked about this idea before. So we have two plates coming together, and you can see how they basically kind of crumple up the land in this area where this was a straight line, but because of these coming together, this gets all kind of crumpled here, right? And of course, the rock underneath there is going to get crumpled as well, and there's where you get sort of syncline or anticlines there and synclines there, right? You get the rock all kind of deformed and warped. Now, as you can see, this kind of causes these mountain ranges to happen. And a great example of that that's in our state of Virginia is the Appalachian Mountains. So this is what the Appalachian Mountains look like. And on a map, you can see this idea that the Appalachian Mountains really do kind of look like the land has been kind of crumpled up like a piece of paper here, right? And the whole idea here is that this part here and this part here were kind of moving towards each other and coming together as a converging plate boundary. Okay, so we get this idea of ridges and valleys formed and the mountains of the Appalachian Mountains forming in that area. And this is actually a picture from the Appalachian Mountains, and you can see that that's happened there. We have our syncline there and some anticlines there. We can see that this kind of looks like it's been crumpled up. Think about what we've learned about before. This is a picture of a Grand Canyon. We've seen the Grand Canyon quite a few times. And we know that normally speaking, layers of sediment are laid down in flat horizontal lines, right? We can see all these flat horizontal lines here. So this is an area where this faulting and folding did not happen. You do not have this stress happening and plates kind of crashing into each other and forming all these folds. Here's what that would look like. Here's what the Grand Canyon would look like if it went through that, right? So we see these layers before that folding process, where the folding process hasn't taken place, and we see these layers after the folding process has taken place. So when this happens and you get folds in the crust of the earth that forms a mountain range, like the Appalachian Mountains, there is a word for this, and we call this an orogeny. An orogeny, that's how you pronounce that. I know that's kind of a weird word that you probably haven't heard of before. So mountain ranges formed by folded crust caused by converging tectonic plates. Now hold on a second. If you've been paying really close attention, and if you really know what you're talking about right now, you should be thinking that something's not quite right here, because here's where we are, right around this area here, right? That's where we are. And if you look at this carefully, what you see is that, first of all, there is no plate boundary there. The plate boundary is way out here. And this is also not a converging plate boundary. If you really know what you're talking about, you should know what this is right here. Right? This is the Mid-Atlantic Trench. And as we've talked about, this is a diverging plate boundary right here. These are going apart from each other. So how the heck do we get this converging mountain forming orogeny in this area? What kind of sense does that make, right? We see on the right here, it's convergent boundaries that cause mountains. Divergent boundaries, they don't do that. They might cause a volcanic chain of mountains here, but that's a totally different thing than kind of crumpling up and deforming the crust of the earth. Okay, so no, I'm not going crazy. No, I'm not wrong about this. I want you to take a look at this video clip that's coming up here, and I want you to pay very close attention to what's going on here during a particular time period, and it'll say it on the video clip as you're watching it. It'll tell you what to pay attention for. But what you're going to see here is a video clip that shows the formation, the movement of the tectonic plates over the last 600 million years. And what you're going to see happening here is actually the formation of Pangaea. Because remember, before Pangaea, there was other supercontinents like Laurasia, right, and Gondwana. So we're going to see the formation of Pangaea, and what you need to look at is when that formation happens and when things are coming together, and then kind of follow what you see going on in the middle of the screen and keep following it until you start to recognize the continent of North America. And what you're going to see is that you'll follow these kind of mountains that were created way back about 370 million years ago, back when that supercontinent of Pangaea was formed. So take a look at this and try to follow that all the way through. All right, so did you see it? Right around 370, 340 million years ago, somewhere around there, these two supercontinents kind of came together and they formed that orogeny then. After that happened, then the North America continent started to move its separate way. We started to pull apart here, right? And move in those directions. And this became sort of the east coast of America right here, and that's where the Appalachian Mountains are. So this happened a really, really long time ago. This happened before even Pangea. So we're talking about hundreds of millions of years ago when this happened. So if you ever go to the Appalachian Mountains, just think about how long ago. It was probably about 300 to 400 million years ago that area was formed, and then it separated away from the other part of the continent and formed sort of the close to the east coast of the United States. Pretty interesting stuff there. All right, so that's what we need to know about folds. Now let's talk about faults. Well, this is when a break or a crack happens where movement occurs. This is when there is basically too much stress on those rocks. And just like when you were putting your hands together and sliding one up and one down, if you keep doing that, it's going to build up some stretch, and your skin will start to kind of stretch and stuff like that, and it builds up stretch, but eventually your hands are going to move, and that's when the fault happens. So this is a very interesting picture here. This is a place called Wallace Creek, and what I want you to look at here, this is a river system that basically is on the San Andreas Fault. And so here's the San Andreas Fault running horizontally across the picture here. And here is part of the river system that was coming through. And here is the rest of the river system after the San Andreas Fault. And you can see very clearly, it definitely seems like these two parts of this river should have been lined up. And so the thing is, this side of San Andreas Fault has moved about 100 yards that way, and this side of San Andreas Fault has moved about 100 yards that way. So this is the size of a football field right here, right? So, okay. And now the water kind of flows through it like that. So here's an example of a fault that has happened. You can see the crack in the ground. Here's another fault. We can see the big crack in the rock going through all the way through here, right? So let's take a look at a few examples. We had a few examples of folds. Now we'll have a few examples of faults, because there's different ways that the ground can be moving in order for this to happen. Think back to the idea of our different plate tectonic boundaries, right? We could have divergent boundaries, convergent boundaries. So think about the fact that they can move in different ways, right? So first of all, we have what's called a normal fault. This is the idea that the two plates are moving apart from each other. So this one's going this way, and this one's going this way. And when that happens, you tend to get this movement of the ground that this part kind of slides down this way. If that's confusing to you, don't worry. We're going to kind of I'm going to have you try that out in class, and you'll see exactly how that works. But this part tends to kind of fall as these guys are moving away from each other. Kind of looks like this. One more time. There you go. Here's an example of a normal fault, right? Take a look at this little picture here, and you can see that this part of the land is up higher than this part of the land. Well, the higher part is up here, way at the top of what looks like a mountain here, and the lower part is here. So think about it. This part of the land right here actually was up here and fell all the way down here. Here's another example of a normal fault. Again, you can kind of see that this side has fallen down compared to the other side. And how do we know that? Well, let's look at the rock layers. Look at the color of this layer here, right? This kind of matches up with this part up here. And if we look, this part right here should kind of line up with this area up in here, and this whole area here should line up with this area in here. So we can tell that there's been some downward movement on this side over here. Here's another example here, right? Again, here's our fault, and we can see the downward movement on this side, right? This layer really should be lined up here. And one more here where you can very clearly see how the one layer has kind of moved down on this side. This layer here should line up with this layer here, right? All right. Next one is a reversed or thrust fault. You can call it a reverse fault or you can call it a thrust fault. This is caused by compression forces. In other words, the forces are going towards each other. The two plates are going towards each other. And it causes the crust to move in sort of an upward direction. So let's take a look at some examples of this. Here it is in action. There you go. Poor tree got knocked over. One more time. All right. So as these are pushing towards each other, that's going to tend to make this kind of move in an upward direction. Okay, so we have a thrust fault here. You can see this part of this rock here has kind of moved out in this direction. This is actually a thrust fault on Mercury. You can see it right there. Here is another thrust fault. Again, we can see here is the fault line right here, and we can see how these layers have kind of been moved up. If you look at this layer kind of in here, that should line up with this layer right here. So you can see that that part has moved up there. Here's another good one. This whole entire mountain looking thing here has been thrusted up in that direction. And here's another nice one. We can very clearly see it. Definitely looks like, you know, this rock was kind of down that way before, but has moved up in that direction compared to this area down here. All right, our last one is going to be called a strike-slip fault. The crust moves alongside each other in opposite directions. So now this is kind of, we got to look at this a little differently here. This is a top view, looking at it from like a bird's eye view, okay? And you have one part of the crust moving this way and the other part of the crust moving this way, just like in this picture here. One part of the crust moving this way and one part of the crust moving that way. And here's your animation, and there it is, right? A strike-slip fault moving side to side. So you can see that here, made those train tracks get kind of messed up. You can see it here, it made the crops get kind of moved to the side. Those crops used to actually be in a straight line. And an example of this is something that we talked about in the beginning of the video. That is the San Andreas Fault in California. So you have the Pacific Ocean plate is kind of moving kind of this way. These guys, we can think of these as kind of moving apart from each other usually. But really, if you look at it in a little bit more detail, they're kind of moving like that, not exactly apart from each other, but sort of this way towards each other. So they're moving, one's moving kind of more northern, one's moving kind of more southern, and they're kind of moving away from each other. So that is the San Andreas. And here we have an actual picture of San Andreas Fault, and you can see that one side of the fault is moving in one direction and the other side is moving in another direction. Again, a strike-slip fault. So let's see if you can name these. What's that one? Normal fault. What's that one? A reverse or thrust fault. And what's that one? That is a strike-slip, or also called a lateral fault, but we'll probably try to stick with the strike-slip name. All right, so this all leads us to the idea of earthquakes. The end result of all this sort of moving around of the Earth's crust is that sometimes you get some violent shaking of the ground after all of this stress has built up and then gets released. Again, go back to that idea of putting your hands together and trying to move them, right? If you do it kind of in the right way and push really hard on your hands together and try to move them, what you see is there's a bunch of stress that builds up and then it kind of all releases and everything moves. Well, that's what happens in an earthquake. Now, You may remember a very specific earthquake that happened in 2011 that happened in Virginia, and here's some little some little pictures of it here. It actually put some cracks in the Washington Monument. You can see one of the cracks right there, and another one right there, and another one right about there. So, an earthquake is the shaking of the Earth's crust from a sudden release of energy in tectonic plates. So this is what's known as elastic rebound, and this is exactly what I was talking about with sort of putting your hands together and trying to move them. You have the rock is being deformed by tectonic activity, these are your folds, and then springs back and releases the energy. Now, the place where the earthquake starts, there's actually sort of 2 points that we can look at. So the epicenter is the point on the Earth's surface that is directly above the focus, and the focus is the actual start of the point of the earthquake, and that's underground, and you can kind of see that in this picture here. So is that the epicenter or the focus that that arrow is pointing at there? Yeah, that's the focus right there. The epicenter would be kind of like where the house is. So the way that they figure out where the epicenter of an earthquake is by what they call triangulating where it is. And that you might look at this and see circles here and say, why is it triangular? Why is it triangling and not circling? Well, tri means 3, right? And so we have 1, 2, 3 circles there. And so the idea is that each one of these is a station where they can read where the waves of the earthquake are coming from, and they can tell how far away they are. The problem is they don't know what direction they are coming from. So here's the idea. For this station right here, they know that it's 1900 kilometers away, but they don't know what direction. It could be 1900 kilometers this way, or it could be 1900 kilometers this way, or it could be 1900 kilometers this way. They really don't know, but what they do know is that you can draw a circle around that point that's 1900 kilometers in radius, and that will give you all the possible places where it could be. Well, if you do that with 3 more places, what you find is that there is one spot where those 3 circles intersect, and that is where the epicenter of the earthquake is, because that is the only spot that is 1900 kilometers from this one, 2,700 kilometers from this one, and 3,400 kilometers from this one. That is the only one that is the right distance from all 3 places. And that's how they figure out where an earthquake started. So in an earthquake, you have body waves that move through the inner part of the Earth, while surface waves travel over the surface of the Earth. As we said before, the way that we figure out the layers of the Earth and what's inside the Earth is by measuring those body waves. So, 2 types of earthquake waves that we need to know about. We need to know about P waves. They are called P waves because they are the primary waves. These are the guys that get there first, and these move in a lateral direction. And if you don't know what that means, well, that's what it means. It means that they move in sort of a squishing kind of fashion. This is also what's known as a compression wave. So the ground is actually moving kind of in that way. If you've ever played around with a slinky and taken the slinky and kind of stretched it out and then moved your hand really quickly in that direction, you would get this type of wave. So that is the direction of the movement of the wave and the particles as well. Now, an S wave is the secondary wave, and these are the guys that get there second. These are stronger and they move back and forth like that. Like if you took a slinky and moved your hand up and down instead of in that direction that I was talking about before, you would get one of these S wave type of motions, and these are the really bad ones. So they have that kind of movement to them. So is this a primary wave or a secondary wave, a P wave or an S wave? Yeah, that's an S wave there because it's moving kind of in an up and down or side to side kind of way. Primary wave or secondary wave. That is a B wave, a primary wave. It is moving kind of back and forth. All right. Next up is how we measure earthquakes. So you guys have probably heard this before. You've probably seen images like these little kind of lines and stuff like that before, right? When they measure earthquakes, and you may have heard of the Richter scale and things like that. So here's how we measure them. We use something called a seismograph, or what is also called a seismometer, but we'll stick with seismograph. This is an instrument that is used to measure the shaking caused by an earthquake. Now, this is what they looked like for a long time, but come on, this is like the 21st century, right? So now they actually kind of look more like this, and they're connected to a computer system, and these guys can measure very, very small amounts of movement and can be very precise. So usually what they do is they dig a little hole, they put a bucket in there with this seismograph in there that's hooked up wirelessly to a computer system that can read what's going on there, and they have these things placed all over the place, especially in places that have a lot of earthquakes. Now, the scale that we use to measure an earthquake is called the Richter scale. And this is a scale for measuring earthquake magnitude, or how powerful the earthquake is. And the thing about the Richter scale that you have to understand is that this is what's known as a logarithmic scale. It's not really necessary that you know that word, but what you should know is that what a logarithmic scale is basically each number on the scale is a multiple of 10 more than the previous number. So a magnitude 7 earthquake generates 10 times larger amplitude waves than those of a magnitude 6. So 1 is a certain strength, 2 would be 10 times stronger than that, a 3 is 10 times stronger than that. So let's see, think about this. How much stronger is a magnitude 3 earthquake than a magnitude 1? Well, that would be 10 times from 1 to 2 and 10 times from 2 to 3. If you're thinking 20, that's not quite right. We're multiplying here. We got to do 10 times 10. So what that means is a magnitude 3 is 100 times more powerful than a magnitude 1. A magnitude 4 would be 1,000 times more powerful than a magnitude 1, and a magnitude 5 is 10,000 times more powerful than a magnitude 1 earthquake. This is another word that I just kind of want you to know. We'll kind of see some video about this in class, so this will get explained a little bit more. But if you look right in kind of these areas here, you can see that this is actually water in here. This is sort of a liquidy kind of thing going on here. Liquefaction is a very odd thing. It's this process where sand changes into basically a sort of dense, gooey liquid kind of stuff and comes bubbling up from the cracks. So this basically happens because of all the shaking that's going on. It creates a situation where the sand mixes with the water underground and creates almost like a quicksand kind of substance. It's like this very liquidy kind of sand. Really kind of weird stuff when this happens. Like I said, we'll see some videos about this in class. Let's talk about preventing earthquake damage. This is a really important idea. Before we go too far with this, we've talked a lot of times about the idea of how certain things, certain types of natural disasters, or possibly some man-made disasters, things like climate change and things like that, and things like weathering and erosion and all that kind of stuff, and river formations. We've talked about the idea of how these things affect poor countries relative to how they affect rich countries. And I want you to think of the idea of how an earthquake would affect a poor country versus how it would affect a rich country. This is a really big deal. Within the past 10 years or so, depending on when you're watching this video, but within the past several years, there have been a couple really major earthquakes. And the two that I'm thinking of, there was one that happened in Japan and one that happened in Haiti. And there is a huge difference in wealth between those two countries. Japan is basically per person is one of the richest countries in the world, whereas Haiti is pretty much on the opposite end of the scale. Haiti is one of the poorest countries in the world, and both of these countries had some pretty major earthquakes in recent memory. And the thing about that is that Japan was much more prepared for these earthquakes because of the fact that they have a lot more money to put into building buildings and things like that in order to prevent the destruction that happens from these earthquakes. And so even though the earthquake that happened in Japan was actually a stronger earthquake, the earthquake that happened in Haiti actually killed a lot more people, and that all comes down to the idea of how much money those countries have and their ability to put in these preventative measures into their buildings and things like that, and into their infrastructure, so that not as much damage happens. So this is a pretty interesting looking thing here. What do you think this is? Yeah, that's kind of a tough one, huh? Well, this is actually a picture of a giant counterweight that helps limit the shaking of a large building. And this is actually in one of the largest buildings in Japan. It's in downtown Tokyo. And what happens is, as this building sways back and forth, the ball kind of stays where it is. And I'll show you some demonstrations of this in class. But basically, when the building moves that way, the ball kind of counteracts that by it's staying where it is, but you can think of it as kind of moving the other way. Okay, so when the weight of the building is wanting to move that way, you have this huge weight that's kind of counteracting that and moving in the opposite direction. This is a pretty amazing way of making sure that a tall building doesn't fall down in an earthquake. You also have situations like this where you can have something where it has like a movable base. So as the ground is all kind of shaking back and forth down here, this whole building can kind of stay where it is while it does that. Here's another example of that, and here's an actual picture of one of those devices. Let's talk about tsunamis. So this earthquake that I was talking about that happened in Japan caused a really bad tsunami. So we need to figure out what the connection here is between these two things. So what is the connection between a tsunami and an earthquake? Well, this is basically what happens when an earthquake happens underwater. And there's the stress and there's the release. Remember, we talked about this idea of the crust being deformed and then releasing all that pressure all of a sudden. Well, when that happens underwater, you create a huge wave in the water that moves along the surface of the ocean. Now, when you think of this wave, and we'll see some video of this, of what happened in Japan, it's probably not how you picture it, because it's not a really tall wave, it's a really wide and long wave. And this creates, it's not something that's quite as impressive looking when you look at it. It's not like this huge tall wave, but it is basically a mountain of water. It is a lot of water that ends up washing ashore that causes a huge amount of damage. And in Japan, this was particularly bad because it actually got to their nuclear power plants, and they almost had a bit of a meltdown with the nuclear power plants. So tsunami is an ocean wave that is generated by a submarine or underwater earthquake. Not a submarine like the ship, but like submarine meaning underwater. And it can also be caused by volcanoes or landslides. This is an animation showing the 2004 Indonesian tsunami that traveled across the Indian Ocean after an earthquake. And here is where the epicenter of the earthquake that happened in Japan several years ago, back in 2011. The earthquake happened right there, and within just a few minutes, they had this huge wall of water that was rushing into Japan and did a really massive amount of destruction to Japan. It was really pretty bad thing for Japan. After this earthquake happened, the plate actually moved 8 feet closer to the North American plate. That's a huge movement, 8 feet of thousands and thousands. Actually, thousands and thousands is not even the word here. Tens of millions of tons of rock all of a sudden moved 8 feet. That is a massive amount of energy and a massive amount of movement of Earth. So this was actually a thrust or reverse fault that made this happen. So what's wrong with calling a tsunami a tidal wave? Well, you should know this, right? Tidal waves are caused by tides, right? They're caused by the pull of the moon and the sun's gravity. This has absolutely nothing to do with tides, so let's just get rid of that word tidal wave and not call it that anymore. The correct word is tsunami. So you guys know This is what causes tides, not earthquakes and things like that. All right, so we talked about the movement of tectonic plates against each other that causes the plates to fault and fold. We talked about some different types of folds, which include synclines, the smiley faces, and the anticlines, which are the frowny faces. And we talked about orogenies, which are mountain ranges formed by folded crust caused by converging tectonic plates, which caused the Appalachian Mountains, but way back a long time ago, right, before Pangea. We talked about a few different types of faults. We have normal faults, reverse faults, and strike-slip faults, which an example of a strike-slip fault is the San Andreas Fault in California. We talked about earthquakes. Speaking of California, they have lots of earthquakes. This is the shaking of the Earth's crust from a sudden release of energy in tectonic plates. We talked about measuring them with seismographs and the scale, which is the Richter scale, which is a logarithmic scale, which means each number is 10 times more powerful than the last number. We talked about this weird thing called liquefaction, and we'll see more about that later. We talked about tsunamis and how they are created by earthquakes or possibly volcanoes and landslides. And we will talk a lot about this more in class, and I will see you then.